Okay, so I've been talking a lot about the connection between zeros and roots and all of that stuff. Um, so again, we're just going to state it out here. If you have a polynomial function, then the following statements are all the same, right? They're all equivalent. So if you have some c value, right, and if we can say c is a zero of that function, then c is also a root or a solution of the equation when you set that equal to 0, right? Zeros, roots, solutions. We can also talk about the factors, right? Now that we've been factoring these out. So we can say the quantity x minus c is a factor of the polynomial function, because when you solve it, that's when you get c as an answer. And if it's a real number, then we can say it's an x-intercept. Sometimes we get those complex numbers, those imaginary numbers, so it's only an x-intercept if it's a real number. But again, this should not be news to you because I've been talking about this a lot throughout the year. All right, so if we have this equation here, x squared minus 4, well, we could solve that, right? So down here I have a little place where we solved it, so I could add 4 over and I would get x squared equals 4. I could take the square root of that, and I actually would get 2 solutions. I would get plus or minus 2. So we could say this about both positive and negative 2, but let's just pick one. So I just picked positive 2. So I can say all about this function. I can say I know that 2 is a 0 of this function. I can say that I know x minus 2 is a factor of this function, right? Because this would factor into x minus 2 and x plus 2. When I solve this, I could say 2 is a solution or is a root. And since it's a real number, I can say that the point 2, 0, or 2 is an x-intercept of the graph. And again, being able to use these words fluidly, like knowing how to go from one to the other, knowing that they mostly mean about the same thing, really, really important. Like shows a really good understanding of algebra. So the fundamental theorem of algebra says what kind of we've been talking about the last few days is that every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. There's a second part to this, which is kind of more important, but it says if you have a function that has a letter in it, right, that's going to be bigger than degree 0, then it has at least one root in the complex number system. It might be imaginary, but it's going to at least have one answer. So look at these problems here. It says solve each equation, state the number and the type of roots. So number 1, that's just a linear equation. But if I solve that, I could add 10 over, and I could say that a equals 10. So that's one solution, and it's one real solution, right? Because that's a real number. Number 2, I could do the quadratic formula here, but I could also just factor this and say what multiplies to give me 48, that subtracts to give me 2. That would be 8 times 6. So I would want a positive 8 and a negative 6. Yeah, so when I solve that, I would get x equals negative 8 and x equals 6. So that would be 2 real solutions. Look at number 3. Well, this is not a trinomial, but I could do a GCF on this, right? So I could take a 3a out of this, and I would be left with a squared plus 6. So I set each part of those equal to 0. Right? So if I divide by 3 here, a number divided, 0 divided by a number is always just 0. And then this one, I could subtract that 6 over, and I could take the square root, and I would get plus or minus I, that takes the negative part out, square root of 6. So look on this one. I have 3 solutions, because remember plus or minus means there's 2 there, a positive and a negative. So I have 3 solutions, but on this one, 1 is real and 2 are complex, or you can say imaginary. Complex is what the book tends to say. Look at the 4th one here. What do I do on this? Well, this is a difference of 2 squares. So what multiplies to give me y to the fourth is y squared and y squared. What multiplies to give me 16, that's a perfect square, 4 and 4. And to get 0 in the middle, one would be plus and one would be minus. So on this one, if I set it equal to 0, I would get negative 4. And on this one, I would get positive 4. So when I take the square root, I get plus or minus 2i on that one. And when I take the square root here, I just get plus or minus 2. So I have 4 solutions, or 4 roots. But on this one, 2 of them are imaginary and 2 are real. Or 2 of them are complex, I guess. So these 4 problems, right, that, like, what makes algebra keep getting more and more, difficult maybe, is that you have to be able to look at these problems and know how to solve them. Because we have a lot of strategies. Do I factor? Do I do GCF? Is it a difference of squares? Is it a sum of cubes? Do I do the quadratic formula? And that's part of what we're going to practice this week, is trying to get better at that. The second part to the fundamental theorem of calculus, sorry, just kidding. We do that in calculus too. Fundamental theorem of algebra, I think that it's the important part, says that if you have a polynomial of degree n, right, then it will have exactly n roots. And that includes repeated roots, so you got to kind of be careful on that. But whatever the degree is, you should have that many solutions. So a degree 3 function will have 3 total answers. A degree 4 will have 4. A degree 5 will have 5. And so just kind of keep that in mind as you're solving these equations. You know how many answers you should be getting. And just a reminder about the repeated roots, right? Like if you had a problem like this, where it went down and touched the x-axis and came back up, we'll say that goes up. That's a repeated root. And so even though this only crosses 1, 2, 3 times, that one counts double. And so that one would be 3, 2, 3, 4. That would be at least 4 solutions on that one. That's what I mean by that. Okay? So the last thing I want to talk about is this rule called Descartes' rule of signs. And I know it looks like Descartes, but it's Descartes. So the S's are kind of silent. René Descartes, I think I have a picture of him in my room here. He did a lot of stuff with math, but one of the things he did, he gets his name on. It's called the rule of signs. And there's a lot of words here, and I used to make people write this out, but I just want to practice it with you. So it says if we have a polynomial function with degrees, with real coefficients, then the number of positive real zeros is the same as the number of changes in sign of the coefficients, or less than this by an even number. And the number of negative real zeros is the same as the number of changes in sign of the coefficients when you plug in negative x, or less than this by an even number. What this does is it gives us a list of how many possible positive real zeros, how many possible negative real zeros, and how many imaginary zeros we could get as we're doing this. Okay, so let's look at an example, and I'll show you what I mean of this, and then we'll practice this in class. So it says, state the possible number of positive real zeros, negative real zeros, and imaginary zeros. And again, eventually, by the end of this week, we're going to be solving these equations. So kind of knowing how many should be positive, how many should be negative, how many should be imaginary are helpful. So what Descartes' rule of signs says is for positive zeros, what we're going to do is we're just going to look at the signs of the coefficients. So notice that I start with a -1 here. So I'm just going to take the signs out, forget about the x's, forget about the numbers. So I'm going to say negative, and then the next sign is a positive, and then a negative, and then a negative, and then a negative, right? And all I did here, and you don't even have to rewrite these when you do it on your paper, but I just wanted to show you, that's what it means by the number of changes in sign. So then you just count. How many times did this function change sign from positive to negative or negative to positive? So it changed right at the beginning, right? From negative to positive, that's 1. And then it changed back from positive to negative, that's 1. And then it stayed negative the rest of the way. So we'll say this changed 2 times. And here's where it's just a possible number, because this is what Descartes figured out. Let me close that out. So it's equal to, so it's the same as the number of changes in sign, or is less than this by an even number. So what that means is when you count the number of changes in sign, you have to count down by 2 until you get to 0. So this means there could be 2 positive real zeros, or there might be 0 positive real zeros. All right, so there could be 2 or there could be 0. So if there's 1, that means there's a second one. That's kind of what that's telling me. All right? So then what does Descartes' rule of signs say for possible negative real zeros? Well, for negative real zeros, they want us to plug in a negative x. Now, this doesn't mean you should actually have to go in and do this. You should be able to use your rules of exponents to think about it. If I take a negative number and I take it to an even exponent, is that going to change the sign, or is that going to leave it the same? If it's an even exponent, it'll stay the same, right? Like that's still going to be a 1 when I do that. But if it's an odd exponent, so if I plug in a negative, I'm putting -1, but negative x works the same way. If I take a negative number to an odd exponent, then that will always leave me a negative left over. That would be -1. So when I do these, I just look at the exponent. So for x to the 6th, a negative is not going to change what that sign is. It's going to stay the same, so it's going to stay a negative. What about this one? It's positive 4x to the 3rd right now. When I plug a negative into that, it's going to change it. So that's going to change from positive 4 to negative 4. What about this one? If I plug a negative x in here, nothing's going to change, right? It's going to stay the same. So that sign in front is going to stay negative. This one's an odd exponent, so if I plug a negative x in there, that's going to change that to positive x. And the number at the end doesn't even have an x in it, so it's never going to change. So for me, I don't actually do the work on this. I just think even exponents keep the same sign, odd exponents change signs. And please write questions if you have them, and we can talk about this in class tomorrow. But it's all about those exponents, whether they're even or odd. And then if you do that, it's the same now as up above. We're just going to count how many times did it change sign. Negative, 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 positive. So it changed here, and then it changed again here. So this one also is 2 or 0, because we have to count down. Negative real zeros. Now, there's not a rule for imaginary, but here's where we can use the fundamental theorem of algebra to help us. How many zeros should this graph have, or this function have? Well, it's the degree of the function, right? So this means I should have 6 solutions when I'm done. So here's where we can kind of set up a chart to do this. And so I kind of just work it out. So like if I want to figure out the imaginary, think of your options. If there are 2 positive and there are 2 negative, how many are left from the 6 answers to be imaginary? 2, right? Because 2, 4, 6. But what if there are 2 positive and 0 negative, right? Because it's or. Well, 2 and 0, how many are left down here? That would be 4, right? Because 4 plus 0 plus 2 equals 6. And then the third option, right, well, we could say 0 and 2, but that would still give me 4, right? What if there were 0 positive and 0 negative zeros? How many would be imaginary? Well, all 6 of them would be imaginary. All right, so you have to kind of do some thinking on that to get those. And as we solve these, that's our next step. This kind of comes in to play. Okay, so we're going to do more of these in class tomorrow. So I'm going to stop talking because I've been talking a while.